Did you channel your inner Gauss? Because it's a little bit challenging to think about that whole number of terms thing, and I'll share with you my rationale that I think kind of mirrors what Gauss thought in his own rationale, and hopefully you can follow this logic. If you're not really sure where this is coming from, I should definitely make the disclaimer right now. Please don't fret too much about this whole idea of deriving the formula. At the end of the day, we're going to finish this video with a formula. The formula will work for every problem in number 5. And as long as you understand how to use the formula, that's the most important part. All of this showing you where the formula comes from is honestly not the part that you're ever going to have to remember. It's not the part that you're ever going to be assessed on. The end result is we know the formula and we can use it. But the reason why I'm walking you through this whole formula development process, again, to reiterate, is so you can understand how mathematicians come up with these things. Formulas weren't just things chiseled on tablets that we inherited from old Babylonians from decades and centuries and way, way, way long ago. Formulas came from somewhere. Somebody made a formula at one point that we now end up using and memorizing, but that original person came up with an idea. That original person noticed a pattern and refined their formula until they got something that actually worked, something that everybody could use, something that everybody could reliably say, hey, yeah, I know how to plug numbers into that thing. So the formula development process isn't just this magical thing that some people are born with and everybody else just has to say, well, I don't know where they got that from, but okay. The formula development process is something every mathematician really should understand, or if nothing else, appreciate. It's hard to develop your own formula. It's hard to think like a mathematician in this way, but it doesn't happen in a vacuum. Mathematicians train their brains to think about formula development, and this is probably the first time that you really had to think about a formula development exercise like this in this class. Maybe in previous classes like geometry you had to think about where the Pythagorean theorem came from, or in Algebra 1 maybe your teacher asked you to think about where the quadratic formula came from, and it's that same kind of thinking. Somebody made that thing up. Somebody came up with that formula. Where were they getting their ideas from? How did they figure that out? And that's what we're doing here. Somebody came up with the formula for the arithmetic series. So we're thinking like that somebody did way back in the day. And we're thinking in the same way they did. Before the formula existed, how did they get the answer? How did they do it? And let's see if we can take their path. So as we left off, the challenge was the total number of terms. That we said, ooh, it's really hard to just know that. If we're counting by ones, the total number of terms is easy. It's just the last number. So the integers from 1 to 20, I have 20 terms. The integers from 1 to 50, I have 50 terms. But if I'm counting by twos to get to 20, that's actually 10 terms. How would I have known that? Or if I'm counting from 15 to 205, how many terms is that? I don't even know how many terms that is. I still don't know. But here's how we can figure it out. Let's think logically for a second, again, about an example we feel sure about. We feel sure about the integers from 1 to 20. We know that there are 20 numbers. How could we know that? I mean, again, to you it might be obvious, but when you really think about it, let's think for a moment. To think about the integers from 1 to 20, most people probably think about the gap from 1 to 20. That if I had to jump from 1 to 2, to 2 to 3, to 3 to 4, to 4 to 5, to 5 to 6, all the way to 20, how many jumps would I have to make? And most people probably naturally just think about the distance from 1 to 20. Distance makes some people think of the word difference, 20 minus 1. But that's a little misleading, because that's not actually true. 20 minus 1 is 19, but there are 20 terms. It's actually one more than that. And when you think about something like the integers from 1 to 50, think about the distance from 1 to 50. Distance or difference. The difference from 50 to 1 is 49. Oh, wait, no. There aren't 49 terms. There are 50 terms. I know that. It's one more. 50 minus 1 is 49 plus 1 is 50. Yeah, 50 terms. Okay. Now here's why that's coming in handy here. Think about question number 4. We want to know what's happening from 2 to 20. So naturally, I want to think about the distance from 2 to 20. The distance, or difference, from 2 to 20 is 18. But wait, I don't have 18 terms here. I know that. Oh yeah, it's because I'm skipping every other term. I'm really counting by twos. If I divide by 2, then I tell myself 18 divided by 2, that's 9. Oh, that sounds more reasonable. But wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There aren't 9 terms, there are 10. Oh, but that's the same thing that keeps happening. I keep ending up, when I subtract, 1 short. So I just have to add an extra 1. 9 plus 1, 10. Yep, 10 terms. I know there are 10 terms. Now, if you're looking at this going, like, what is she doing? Let me just quickly explain again what I'm thinking about here. I'm thinking about the distance between the terms. So from the first to the last, I'm thinking about that distance or difference. I'm thinking about what I'm counting by. And then I'm acknowledging it's always 1 extra term there at the end. That distance doesn't quite give me the exact precise number of terms. I always have to add 1 to get the exact precise amount of terms that I know I need. So then you might be asking yourself, well, Herbert, why did you do this little divide by 2 in number 4? What was that from? Why didn't I do that before? Think about it. I was skipping every other term. So the distance from 2 to 20 wasn't really that helpful because I didn't want every number between 2 and 20. I wanted every other number, or dividing by 2 to show that it's really every second term, or every second value that I wanted. I didn't want all the numbers from 2 to 20. I wanted from 2 to 4. That's every second term. I wanted from 2 to 6. That's every second term. So I'm dividing by 2 to show really this pattern was only taking every second term. If you're thinking, okay, but why didn't you do that in number 3? I technically did. When you think about it, if I was doing the integers from 1 to 50, 1, 2, 3, 4, 5, 6, I'm taking every single term. Every term in between is being accounted for. So even though mathematically it doesn't make a difference, I was technically doing that distance divided by 1, because I was counting by ones. 50 minus 1 is 49. 49 divided by 1 is 49. And plus 1 is 50. There are 50 terms. Same thing in number 2. The distance from 1 to 20 is 19 terms, divided by 1, because I'm counting by ones. Add the extra 1 at the end. 19 plus 1 is 20. So, in general, I do now have a relatively reliable way of finding the number of terms. The number of terms can be found by doing the following steps. First, find the distance or difference from the first to the last term, 20 minus 1. Divide by what your adder is. Divide by what you're counting by, and then add 1. That add 1 is not because 1 is a specific number in the problem. That add 1 is kind of a universal step. So if we were to generalize, the first step was find the difference, or the distance, and I'll make sure that we can read that here. Find the difference, divide by what we're counting by. I'll keep using familiar terminology. I'll call that the adder. And then add 1. That seems to be reliable. That seems to be working. So I'm going to go back to my formula here. Let's see if I can kind of refine this a bit. The total number of terms we're saying, and I'll rewrite this over on the side, the total number of terms has essentially its own little algorithm or its own little formula. The total number of terms is the difference between the last term and the first term. And again, I'll explain my notation, but for now, just notice that's what I'm talking about. It's that difference between the last and the first terms divided by the adder plus 1. Now, this is where things are going to get a little bit challenging. Because remember that this total number of terms thing, this was just the top of a formula that otherwise has a lot more going on. And if I'm thinking about taking this total number of terms formula and merging it together with the formula I already have, I'm starting to think that's going to look really complicated. That to me is starting to look really gnarly. Because if I have a formula that already has a bit of a fraction, and then I have to also do this formula with a fraction, that's going to look kind of messy. So I'm going to propose one of two options for you. as you think about recording this formula for your own long-term usage. One possible formula that you can write is a cleaned up version of what we're saying here, but written with a slightly cleaner notation. Remember how dividing by 2 was part of my original Gauss formula, my original arithmetic formula that was working so well for me? Well, dividing by 2 is the same thing as multiplying by a half. So I'm going to clean this up by saying, okay, the formula is going to be 1/2, that kind of takes care of this, times the sum of the first and the last terms times the total number of terms. And to clean that up a little bit more, 1/2 times the sum times the total number of terms, that's the same formula I had, just kind of cleaned up and looks a little different. That's 1/2 times the sum was the first plus the last term. And the total number of terms, its own little sub-formula here that I already kind of created in my side work, was the difference between the last minus the first. Notice it looks kind of similar to what I have, and that's why I wanted to clean this up with notation so I have some consistency. Divided by the adder. We don't really have a good variable for adder, so I'm just going to keep writing adder plus 1. Now that is a complicated looking formula, but it totally works. That is a very valuable formula that we can use. And because I'm kind of using this pink to indicate formulas here, I'm going to draw a box around this as an indicator. That's something that you can either take a screenshot of or take a picture of or copy down on your own notes. That going forward is a pretty reliable formula for what we call the sum of a finite arithmetic series. And I'll make sure that I clarify. I said the word finite there for the first time. I haven't really said that before. But this is the formula for any problem that involves finding the sum in an arithmetic series. Now this is the part that I said you have to be able to use. Even if you have no recollection of where it came from, this is the part that you definitely want to make sure that you save. This is the part that you want to make sure you write down and record. This is what we're going to use. Now, to prove that our formula works, let's go back and do a problem that we kind of already know the answer to, so that we can prove to ourselves that it's definitely a valid formula, and then we'll apply it in other problems to see that it actually works no matter what. I'm going to go back to my packet, question number 5, and I'm going to do question letter A. The reason I'm doing question letter A is because that's actually Gauss's problem. 1 plus 2 plus etc., 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 up to 99 to 100. That was Gauss's problem when he was 7 years old. That was the problem he was sent to the corner to go do, and that he so smartly came back just a few moments later and could do in his head that his teacher was like, oh, darn, thought that kid was going to take way longer than that. This is Gauss's problem. So let's channel our Gauss and let's prove that our formula works. Our formula is going to be 1/2 times, this is the sum part. The sum is a sub 1 plus a sub n, but really that just means first term plus last term. And if you want to modify your formula so that you know what first and last mean, those are just the notational usages for first and last. I like to use a sub 1 and a sub n just because that's what a lot of textbooks use, but you can just as easily write first and last if you prefer words in formulas instead of writing like actual weird subscripts. In any case, let's translate. First refers to the first term in the list, that's going to be 1, plus last refers to the last term in the list, that's 100. So there's the parentheses there, 1 plus 100. And then next parentheses, sorry, make sure we can see all of this, a sub n minus a sub 1. So it's actually the same two numbers, just subtracted, 100 minus 1, divided by the adder. This is adding by 1, so divided by 1 plus 1. Now, let's do this calculation. 1/2 is obviously just 1/2. 1 plus 100 is 101. 100 minus 1 is 99. Divided by 1 is 99. Plus 1 is 100. Now at this point, if you're like, oh, Herbert, I am not Gauss. I can't do 101 times 100 divided by 2. That's too tedious for me. It's fine if you use a calculator, honestly, just to kind of expedite things a little bit. So 1/2 times 100 times 101. Sorry for the order there. Oops. That gives us 50/50. And sure enough, that was Gauss's original answer. Remember how I did that way back a couple videos ago? That was Gauss's answer. So, we know our formula works. And the moral of the story is, once your formula works, we know that we can use it for every problem. We just had to make sure that we know a few key bits of information. We have to know the first term in the list. We have to know the last term in the list. We have to know the adder, which we can usually tell just by visualizing. And we have to know the whole formula to get the series of steps correct. But let's try one more example. Let's try letter C and make sure that we understand how to use our formula. No matter what the original number is, no matter what the adder is, let's make sure that we've got a pretty good handle on this. Now, of course, for letter C, we need to, and I'll give myself a little bit of scratch space here since I have a bunch of extra writing. We need our formula to work, so let's start plugging things in. We have 1/2 times, and again, I'm going to read off my formula, but I'm going to show more clearly my work so that way you can see it. Refer to your formula if you need to with a screenshot, or write it down for yourself so you can see where I'm getting these from. A sub 1 is the first term, that's 15, plus A sub n is the last term, that's 205. I can tell those things just by looking at the formula. Then I've got the difference, so that's going to be the subtracting part, last minus first, divided by the adder. I can tell just by looking at this sequence is, or series is adding by 10, so my adder must be 10 plus 1. So I'm looking at this, seeing a few tedious calculations to do, but nothing too crazy. Adding, subtracting, dividing, I can do all these things, or you can quickly use a calculator if it helps. 15 plus 205 looks like it's going to be 220. Then I have 205 minus 15, which appears to be 190. Divided by 10 is 19. 19 plus 1 is 20. So I have 1/2 times 220 times 20, which should be 2200. Now again, if you need to use a calculator for this, that's completely fine. If you just did some mental math like I did there, that's fine too. But 2,200 or 2,200 is the actual legitimate sum. So it totally does work. And you can check the answer key to verify that our formula really does work. So going forward then, here's what I'm going to ask you to do. To finish today's lesson, do two things. First, make sure that you write down the formula in a way that makes sense. Initially, when I presented this formula, I actually said that there were 2 different ways that you could write this formula, and I kind of glossed over the second way. But what I want to point out to you here is the second way that you can write this formula is kind of like we wrote it before, as a formula with a sub-formula written separately. So if you wanted to write the formula as kind of a 2-step process, you could have the sum, which again is the A sub 1 plus A sub n, times the number of terms divided by 2, and then make a separate little sub formula, maybe with a little arrow for yourself, with the total number of terms formula written separately. So you'd have to do kind of a 2-step process. You'd have to do this part first, and then you'd have to do the other formula with the pink highlights second, which might get kind of confusing. I don't know how many people are going to love doing that sort of incremental method. So that's why I tend to just stick with this one formula. If you were to take one screenshot or write down one thing from this entire series of videos, it's this one. This is the formula that you would want, because this gives you 100% of the things that you need in order to do the formula or to do the sum without needing to search for extra information. So, first step, write down this formula. Make sure you know how to use it. Second step, finish question number 5. Use your formula to help you answer all of these problems. Check your answers using the answer key so that you can make sure that you're using the formula correctly. It's fine if you use a calculator. It'll just save you on some of the tedious multiplications, but try to make sure that you think about the formula itself. Why are all of the steps working? If you really lost the thread of where the formula came from, please don't panic. I showed you all of that just so you can understand that it wasn't just a mystery. It wasn't just chiseled on tablets from old Babylonian men centuries ago. It really did come from somewhere logical. But if you didn't follow that logic, or if it just kind of ended up being a bit overwhelming, please don't panic. That's not the important part. The important part is that you know the formula and that you can use it in problems like number 5. Because that was a lot to digest in one day, I don't recommend that once you finish question number 5 that you go on to page 10. I think right now would be a great time to just make sure that you digest the info and then finish the page and stop. Once your brain is kind of freed up and really has some time to process everything you learned, then work on page 10 is a separate lesson. Think of page 10 as a whole separate, whole new beast. And if you look at the learning plan, you'll even see that this page was intended to be done on a different day than page 10. Heed that advice, especially if you feel like your head is kind of swimming right now. In any case, if you have any questions, or if you feel like you need to check your answers, go to the answer key first, leave a comment in the Google Classroom, or send me an email. Anything that I can do to help clarify or shed some light on what was going on, I will be glad to help with. But hopefully at this point you can start to take some time to sort of independently work through the process and let the idea sink in a bit.